Mənim adım Jamal Musaev. Əvvəldən bütün təşkilatçılara məni bu vebinara dəvət elədiyi üçün çox sağ ol deyirəm. Öz minnətdarlığımı bildirirəm bütün iştirakçılara da. Məsələn, istifadə eləyib bu böyük zəfər bayrağı, zəfəri Vətən müharibəsində qələbəmizin nəticələrini istifadə eləyib. Məsələn, belə bir institut yaratmaq olar, Science Technology Institute. Bu institut həm graduate level education-la, təhsil ilə, top level sizə, high level sizə belə yuxarı səviyyəli elmi bir yerə gətirməlidir. Niyə Qarabağda siz deyə bilərsiniz? Mən ona görə deyirəm Qarabağdakı, çünki Qarabağda həm Qarabağın inkişafına kömək eləyəcək, Qarabağı dünya açılmağına kömək eləyəcək, həm orada iş yeri yaradacaq, gənclərin oraya qayıtmağına kömək eləyəcək və s. və s. Həm də ki, əgər bunun startup texnologiya parkı zadı olandan sonra oralarda böyük texnologiya parkları da yarana biləcəkdir. Mən bilmirəm, sizin çox, bəlkə də çox uzun əlaqəz var, bilirsiniz. Məsələn, elə bil ki, imitasiya King Abdullah Universiteti, Saudi Arabiyada və ya Azərbaycanda çox aktivli yaradılmış və prezidentin bir həmişə nəzarəti altında olan, məsələn, nizami fondu kimi bir şey. Ancaq bu fond, bu institut Science və Technology Institute. Burada elə problemləri seçmək lazımdır ki, birbaşa Azərbaycanın ekonomikası ilə, Azərbaycanın dövlətin inkişafı ilə birbaşa əlaqəsi olsun. İnstitutda həm Azərbaycanlılar, həm də ki, xaricdən gəlmələr işləməlidir. Əsasla dil də ki, burada İngilis dili olmalıdır. İkincisi də ki, elə seçmək lazımdır ki, top level education, ekonomi Azərbaycana kömək eləyəbilsin. Bunun, mən dediyim, it is a positive outcome, it is going to be tremendous. Necə eləmək lazımdır, həmişə gənclərin, mən sizə deyirəm bunu birincisi ki, çünki gənclər eləməlidir. Vətən müharibəsində də dediyim kimi, gənclərin contribution, gənclərin rolu Vətən müharibəsində çox yuxarı. İndi də bu da elə bir ki, bizim elmi yuxarı qaldırmaq üçün, təhsili yuxarı qaldırmaq üçün bizim öz şəhidlər qarşısında borcumuzdur. Burada da gənclərin rolu xüsusi olmalıdır. Gənclərə xüsusi yol verilməlidir bu cəhətdə. Necə deyərlər, mən öz fikrimi deyirəm, qoyuram sizin çiyinlərinizə. I am challenging you. Let's say this way. Okay? And from this point, I want to go to science and give you a little information. Who I am. People are still coming. Who I am and what we are doing. I'm sorry I moved into English. I will use my broken English. And you don't hesitate and also ask questions. And because I learned all of these things which I am going to talk today, and by doing science myself, it's because my education in Azerbaijan in science is finished after I graduated from university. I moved to Moscow and Japan, and US, etc. And that's the reason. My group actually is theoretical computational group. We use all kinds of theoretical methods to really to explain and work together with our colleagues, design new materials, new catalysts, and new kind of processes. Yeah. Sometimes when theory is not advanced and in the processes which we've been planning to study, in that case, we have no choice while returning back and ourselves and trying to develop new theory. or new type of computational methodology. For example, I will give you later information about our alternative solar energy projects. And on this project is one of critical factors it's the electron transfer between semiconductors and quantum dots to catalyst, both oxidation catalyst in general. Electron transfer processes, as you know, in general, they affect it's important processes in biological processes too. But to deeply analyze these processes, and unfortunately, its theory is not very well developed. Of course, there is a Marx theorem, you know that. Marx gets the Nobel Prize. I know Rudy was in Azerbaijan a couple of times and on these humanitarian meetings and etc. But when you go to actually quantum dots or small clusters, quantum dots is actually semiconductors and small size semiconductors. And this process is not well developed. Lately, we developed a bulk adjusted linear combination atomic orbital approach. We also use this approach to study its co-shell quantum dot. And in other words, this co is for example, this is a gallium selenide, and the shell could be gallium sulfonide, etc. Or I'm sure you are familiar with technology called this atomic layer deposition technology. When you have this, actually, you put the sensitizer or catalyst on the electrode, and if its stability is not very well, actually it has no high stability, then people put on top of that this atomic layer deposition type of technology using additional materials to keep this electrolyte stable. But if this type of things, when the electron transfer take place, these materials which are deposited into this electrolyte, it's also impact electron transfer processes. Unfortunately, these heteroassemblies are not suitable for were not suitable for theoretical approaches. We've been developing these additional theoretical methods. But it's on top of that, and we do it's actually multidisciplinary research, because just doing theory, you can't go too much or very much or achieve something. That's why in my groups, we are actually, multidisciplinarity is a critical factor. For example, my students or my postdocs, they should know theory. On top of that, they should know and chemistry or materials or physics. And this is difficult, but it is actually rewarding. I will give you one example later. And since using this multidisciplinarity, opening up, it is really difficult step. Everybody should make effort, especially if you come in from different scientific backgrounds, and you are talking into two different languages, to using two different type of several different type of terminology, and you need to understand what person is going to tell you and translate it to your terminologies and to your language, and then return it back to them in a way that that person should understand all that. This is actually communication problems. But this, on top of communications, we all are learning something different. And we're using this multidisciplinary approach. My groups involved several projects. One of them is Selective Ch Functionalization. This is mostly methodology, selective Ch functionalization methodology developments for purposes for late state functionalization. It is for more drug discovery or drug design purposes. But this actually, many of you are actually working probably on this area. CH activation is not new problem, but process is really selective CH activation or CH functionalization. For example, even you take this small organic molecules, you see here many different types of CH bonds. For pharma industry or for materials industry, it is critical to selectively functionalize for given CH bonds. Among all this, many of them. Of course, if you use a previous approach, they make a catalyst and put together together with your substrate, very often substrate control which CH bond is going to be. I mean, this chemical or physical property of CH bonds control which one is going to be activated. But that's create a lot of mess. And product which you are getting, it is actually to get many different products, and really it's a mixture. That's nobody is actually, neither it's polymers, no it's material science, no it's a drug discovery, or nobody actually needs this type of reactions. And scientists find way to do this selectively. One of these ways is actually, you guys are, I'm sure you know, a direct and group approach. And you take in your organic substrate or any kind of substrate, first embed in there some directing group. It is first step is actually you do an additional reaction. You put in there a directing group, then coordinating this directing group to transition metal center and control selective CH functionalization or activation. This approach has, I mean, originally this approach actually started about 20 years ago. It's mostly to lead to the ortho-CH functionalization. And this remote CH functionalization, now people are trying to, are making efforts to develop the remote CH functionalization using directing group approach. And actually there are multiple, it is a wonderful developments. One of those, actually, one of my collaborators, Jin Kwan Yu from Scrib Institute, he's leading on this type of things. And David Najib and many others in this area, it's actually pushing these directions. But this directing group approach is a multi-step process. Yeah, you have to put directing group with substrate, and to perform your reactions, at the end of the reaction, you have to remove it. This is a multi-step process. And what's actually another group of people doing, they are using catalyst control approach. And in other words, when you are developing catalyst library, and then you know that which catalyst, which kind of CH bond is going to be activated. For example, if you take catalyst A, it will go to primary CH activation. If you will go to catalyst B, if you will go to the secondary. If you need to tertiary CH activation, oh, this I will take this catalyst which is doing tertiary activation. That's two different strategies actually people are putting together. Of course, these are actually deeply understanding these processes and connecting to this using the computational and mechanistic approach and connecting to these biological processes. And it's really a learning from nature, and it's going to be really open new directions, new type of approach, a new type of catalyst for future CH, selective CH functionalization processes. You remember, it's actually, you know very well, actually, I've been looking your Facebook website. You are given all kinds of the latest developments and also exciting developments in chemistry. You put in some articles there. Even it is Ben List or David Macmillan, they got the Nobel Prize for this organocatalysis. They learn from the biological catalyst. They try to mimic enzymatic catalysis from the beginning, and to use organic species as a catalyst, and just like something like this enzymes. We actually, it's inspired with this type of approach. We would like really inspired by enzymatic catalysts and builds this as a new catalyst for selective Ch functionalization. This is catalyst control type of strategy. Or go to the directing group approach and to do the late, it is a remote Ch functionalization, selective remote Ch functionalization. Of course, we would like later to return back as after learning all this thing, return back to a natural environment and to the artificial metal enzymes. And on top of that, I would like to also use photocatalyst. To this day, photocatalyst is becoming one hot area of the research. And nothing is strange, nothing, it's really, opens new way designing chemical reactions. Why we're going to artificial metal enzymes? We actually take metal enzyme, natural metal enzyme. We know that the active center of this enzymatic catalyst is some kind of transition metal containing species, but the surrounding protein environment actually controls selectivity. We would like to actually keep protein environment as it is and embed this catalyst which we are developing to inside this protein environment, replace original metal centers or metal complexes by newly designed transition metal catalyst. This type of approach is actually combines both advances of biological and synthetic catalysis, and also allows to transform the small molecules to usable products. And really, it's an open new ways. Actually, it's activate or utilize and different substrate, which nature doesn't want, or the nature has no way to do it. Of course, there is a complementary approach to artificial metal enzymes. It is direct evolution approach. Frances Arnold, she got this Nobel Prize 2018 on this direction. Frances Group's approaches actually keep metal enzyme as it is, only changes its amino acids around, or introduce gene mutation, and do screening all these things. This is, I am collaborating one of her, actually it's students, Jared Lewis, and this is very, very tedious process, but Francis, they know what they're doing. This is another, high level directions to go. It is actually allows to really learn changing by amino acid environments in protein environment. You can control certain type of reactions and functionalize. Actually, it's again these materials which is previously was not possible to do. And we want to do it using actually computational guided way, or machine learning way, or you can say multidisciplinary way. We really believe that, and we demonstrated a couple of times. And this type of approach makes things much faster. Success is coming much faster. Of course, I will give you also a little more information. But this is actually learning from nature. I'm returning back to my first slides, learning from nature, trying to do better than nature. What I actually described to you is selective Ch functionalization process. A few advances in these directions. You may say that cannot be done by one group only. My group, usually I like to keep it as small as possible. But yes, you are right. But if you are multidisciplinary, you like communications, you are open to learn others' language and translate, you can do it. That's what we did. Wow, we are doing. We set up new center and funded by National Science Foundation of Emory, America. And this center is a Selective Ch Functionalization Center. And combined together, it's 15 universities, top universities in US, and 22 research groups. I am proud that I am actually one of 5 co-founders of this center. And so you can see it, we have actually from Berkeley, Caltech, and from Stanford, MIT, I mean, you can name it, I mean, 20, Georgia Tech, etc. And also people who are here, they have different type of skill set. Theoreticians only are myself and Ken Houck from UCLA. Others are hardcore experimentalists of different type of experimentalists. When we established this center, then in several pharma companies I listed down, they joined to us at some level because we don't want to really disclose everything before publication, and put partners with us. They put additional funding to this process. And after we established Japanese groups in Japan, in Nagoya, they established similar types of approach by using JSPS or JCTC, it's funding. They call Institute of Transformative Biomolecules. We have close collaboration with these groups, and especially my collaboration goes to this Ken Itami group. And we got, actually, it's amazingly working together. We got 1 international patent for design catalyst for CH amination, CH bond amination. And also in Korea, KAIST, Korea Advanced Institute of Science and Technology, they also set up the new CCHF, Center for Catalytic Hydrocarbon Functionalization. They also recognize importance of this process. We have also close collaboration with Sukbok Chang on this director of this center on CH functionalization, basically using by CP rhodium type of catalyst in our studies. Let me to give you little information to our approach to this. How it's multidisciplinary. This is relatively old approach, old data. It is 2019 is published. We moved too far from in these directions, but I like, since this shows how, if you have multidisciplinary approach, how much you can achieve. I will talk to you, basically it's a fundamental concept, carbine transfer, carbine nitrogen transfer. You know that it is critical processes transferring carbine and nitrogen to CH bonds, or CC double bonds or triple bonds, cyclopropanation or cyclopropanation processes. They are critical components, critical reactions for drug design, etc. And in general, CH oxidation, it could be amination, alkylation, etc., 2-electron oxidation process. Very often, organic chemists, not now, I mean 10, 15 years ago, they didn't like to talk about these oxidation processes or single electron transfer processes or hydrogen atom transfer, etc. They been very much actually, how to say, not to use wrong ways. They've been actually concentrating this, okay, I want to get this reaction done. I want to get this molecule. For that reason, I will try this screening multiple ways how I'm going to get it. But if you will do this from the knowledge, I mean, they are doing knowledge, but I mean, this really it's a computational electronic level knowledge that will actually make process faster and more controllable. And let me give you a little information, this carbine transfer. You know, this is actually, I'm going to talk about actually for simple carbine, not NHC type of carbines, etc. If you got single carbines, one of the sources single carbines could be diazo compounds. You can go to decomposition diazo compounds. Yeah, these carbines has 2 electron states, singlet and triplet electron states. In single electron state, HOMO is double occupied, LUMA is empty. HOMA is sigma orbital, LUMA is pi orbital. Then triplet states, each has one HOMA, LUMA, sigma, pi. They have 1 electrons. And since this is triplet, it's extremely reactive species. It's not stable. And we showed this in 1993. And of course, if you go to singlet carbines, NHCs, you guys are using it as a ligand because it is singlet, it is stable carbene. You can use it as a singlet, as a ligand in your organic reactions, organometallic reactions. Okay. But if you go to introduce some substitution, let's say to replace one hydrogen with R, you are strongly impacting electronic nature of carbene carbon atom, central carbon atom. By doing this donation from this carbene to lone pairs to pi orbitals or any kind of orbitals, R group, or back donation from this, actually it's this R group to pi LUMA orbitals, lowest unoccupied orbital of the carbene center. This, of course, is going to be impact electronics of the carbene center. It is going to be impact to coordination of this carbon to transition metals, etc., or stability of this carbene. And in general, this is a chemist. I mean, this is I will say maybe 50 years already. Developed several types of diazocarbenes, and it is donor carbene by adding donor groups, or donor acceptor carbene by having two acceptor. I think they made mistake here. It's having two acceptor here, acceptor carbenes, or donor acceptor carbenes and donor carbenes, etc. Let me to just demonstrate to you in simple language what we mean. For example, if you go to acceptor carbene, only acceptor, yeah, you have hydrogen, one hydrogen will replace by ester. Ester may have this, actually, it has pi star orbital from carbonyl, and that pi star orbital is empty. It can take electrons from this carbene center. It is donation to there. But it's that, I mean, in ester group, oxygen has lone pair, as well as CO bond has lone pair, it's a pi orbital. They can contribute back to carbene, LUMA pi orbitals. This, we calculated this contribution is much larger than its back donation component. As a result, entire groups you can be characterized as acceptor. It takes, it's actually, you can add characterize as acceptor. It's because carbene accepting more electrons from, from these lone pairs than donating back. If you go to donor group, in this case, or acceptor case, since pi interaction is strong, then this back donation interaction, it leads to rotation of ester groups. Ester group now becomes located on the perpendicular plane to the pi orbital plane of carbene. But if you go to donor groups, for example, some aryls, benzene ligands you put here, it also has two components. And donation from this actually carbene center to benzene pi star orbital, or back donation from the benzene pi orbitals to back to the carbene. You can see this is highly, it's 5 times almost stronger. It means actually this is stronger. Strong is the electron donating group. As a result, since this pi-pi interaction is stronger, it is actually benzene rings prefer to stay in the same plane as a carbene pi orbital. That's just simple information. And also known facts that, the chemists using different type of catalysts to do diazo compound activation, decomposition, and carbene formation. For the diazo activation is really its extrusion of N2 and making the carbene complex. And people extensively use this in literature. It's a dirodium tetracarboxylate type of species, or it's actually there are simple copper catalyst or iron catalyst for these purposes. There are many different catalysts, but rhodium catalyst, which we are concentrated mostly, it is very selective, or we can do selective and high yield. For example, this is one of rhodium catalysts my collaborator is doing. You can go to the 6 million turnover numbers. It is huge. Even rhodium is expensive. I mean, you can use 0.00 something % and do its reactions to Vilgo. First step, as I said, it's well established that you have to activate upcoming diazox species and removing N2, making carbene complex. And next step, you bring either CH bonds or double bond or triple bond, insert this carbene to there. Go back. Insert carbene to there, then to get product. And for this reason, we established that multiple processes are going to be critical, not just electronic nature of the rhodium 2 center, but also ligands surrounding. Surrounding ligands provide additional stability of catalyst during catalytic process, but also generates and pocket, like this enzymatic pocket, I mean, it's a reactive pocket in the enzymes. And then if pocket size is critically important, and also electronic nature of ligands is critically important for coordination of diazo compounds, activation, and carbene formation or carbine transfer. These weak interactions between ligands and carbene actually control selective CH functionalization process. Using this high-level information from computation, and now it's working together with my colleagues, is Hugh Davis, who is actually Hugh Davis. He is actually one of top leaders on this in this field, who published already extended catalyst library. For example, we know that if you want to use a rhodium TPCP catalyst, it will directly go to the secondary CH activation, the functionalization. If you want to go to primary, you need to use the dirodium phenyl TPCP substituents. And if you want to go to tertiary, you need to go actually different catalysts. It is with adamantyl groups, because adamantyl groups is large. It is actually located one side of the dirodium species and really gives very rigid catalytic active center or catalytic active pocket of the catalyst. And we published several papers. I mean, we can go to look at those papers, but also we are still working on this, and we're expanding this library for different type of these catalytic processes. And one example which I want to bring to your attention, actually it's collaborative with my colleague from Georgia Tech, from France, but this, most importantly, this is the achievement of brilliant graduate student, Brett McLaren. And when I'm talking about multidisciplinarity, that's the multidisciplinarity. Brett, actually, he's experimentalist, but he somewhere excited from our research. He asked me to join my group part-time from Stefan's group to do a computation. One of the projects we assigned to him to take accept the carbenes. Accept the carbenes, they are less stable, and that's why very difficult to control their reactivity. And he chose here actually they take this alpha diazomethyl acetate, yeah. And he took this and carbene. He said, Jamal says, I am going to look this RF. One side you have substitution, the substituent is the substituent. Another side you have acetaldehyde. He said, I want to see what's the role of R on this. It is actually aldehyde side. He just started learning. He did his first calculations and tried to analyze, accept the donor properties of carbenes. He sees that actually impact from these aldehydes to carbene center is more critical than from ester center, ester ligand in this case. Then he said, I'm going to take this transition state. He did calculate, he used here the thyroidium, this ESP type of catalyst, which shows extraordinary catalytic activity and also stability. And it looks is actually its insertions is this carbene, beta carbonyl ester carbene to CH bond. And by changing R, by looking R effect on this acetaldehyde side. I also here would like to bring your attention latest paper in Nature Reviews. We put together a large number of people, and I am in charge on the computational rational reaction design sections. And if you have no access, please let me know. I can send you directly this review. And I am sure that this review is going to be some kind of textbook upcoming, or upcoming at least 5-8 years for scientists. And if you would like to have it, either you can go to get it, or we can send you. I can send you. I put there some information about these reactions too. But what Brett did was said, Jamal, first I want to analyze steric electronic effects to carbene center, because that's going to be important. What's the electronics going to behave? Carbene for CH insertion. And steric electronics is important, and really it's electronics, orbitals, carbonyl from this actually aldehyde or ketone side. Is going to be interact with carbene pi orbitals, and electronics sterics is completely unexpected. Was for me came out to me. It is actually Brett. He teach me how to really use organic textbooks. And what he did, first step, he took just beta keta esters with different type of para substituents. He did calculations. And he used just his Hammett principles and analyzed his Hammett principles. He calculated this barrier for CH insertion. He sees it's actually it's correlate with electronic nature of para substituents. In other words, actually you can use Hammett principles or Hammett coefficients really predict for reactivity of this type of species, carbine transfer species. But Hammett parameters are not available for all of the organic substrate which you're going to use, and also it's have a lot of limitation. He said it is too complicated. Let's go to simple way, because we need to give these organic peoples. He, as I said, he's been doing the experiments as well as computation himself. He been going to lab 1 week, getting experiment, coming back to my group meetings, learning terms, giving us information, getting ideas, and going to back lab about again testing things. He said this organic chemist or chemist in general wants to manipulate with really very simple parameters. He said since maybe we can look this actually proton affinity of this carbene center as an electronic factor. He did calculate that proton affinity. He sees that actually it's all parameters for proton affinity is perfectly right. But when you go to steric effects, to take into steric effects, he said, he came up that to use A value. I'm sure you're familiar with A value on this hexene. cyclohexene. And he said, instead, I mean, this A value is not available for all substrates. Let's look this for my carbines. He's been using this, this is the beta carbines. I mean, the distance between R group and is the carbonyl as a parameter, steric parameter. He did try this and did fitting. He sees that this parameter actually nicely reproduce A value from organic textbooks for 98%. But this is more expandable parameter, this distance between R and these groups and the carbonyl from the ester, than A value. But it is not easy to calculate because you have transition metal center attached on this transition state. You have to do transition state calculations. It is too tedious and time consuming. He said, let's remove this transition metal, use proton affinity, it's carbon, and this distance between R and O. And see, when he did, and it is actually it's 98% consistent with A value approach on to transition state. But this is much expandable and easy to compute. It will take just 5 minutes or 10-minute calculations for each substrate or carbene you're going to look. It is, you can do huge library within 1 day. He did this, he took these two parameters, and one is actually its electronic effects, and this he modeled this electronic effect by proton affinity, and steric effect by distance between R and carbonyl, is the carbonyl group, oxygen. He used just mathematics and simple fitting. You may call this machine learning, may call this fitting. Fit this function, these two parameters, calculate this energy of transition state or barrier for CH insertion. And he came up with this chemical space map, divided it into 4 categories. This way, you get in high PI, proton affinity. Here, you get in these directions. Actually, you have steric effect, distance between R group and carbonyl oxygen. You can see actually it's arrow ketones, Q2, and Q1, tertiary amide, etc. They have such larger barriers. Keep in your mind, everything is here relative, okay? And we are talking about relative because all calculations done at same level, but absolute values could be different when you're going to do different level calculations or different expectations. But these two, Q2 or Q1, is actually with larger steric, larger PI, proton affinity, they are not going to be good carbines for insertion CH, same as this one. Good carbines, I mean, easy reaction are going to be Q3, and Q4 element. It is aldehyde, esters, primary amide, and secondary amides. And when he took this, he went to lab. When he made this, he went to lab, he disappeared 1 month because he had to run all validation reactions at least. He did run many. I am not going to talk about all these things, but for us was interesting why tertiary amides are not reactive, but secondary amides, even primary amides, they are reactive. And for this reason, he decided really to validate it. Indeed, when he used this, actually it's a tertiary amide, he sees 0 reaction, no reaction. Barrier is high, proton affinity is high. When he went to it's secondary, he get 84% as his methods predicted. Then he analyzed this transition state structure. It turns out to be in transition states there is weak hydrogen bonding on this primary amine, secondary amine. There is small hydrogen bonding which reduce steric component of this contribution from this air. In another word, this weak interaction, the hydrogen bonding interaction, really impacts strongly outcome of this reaction. He was so excited. He wants to make one more step. He uses different type of secondary NRL alpha diazer beta amides, and here, indeed, he sees this actually by changing R, impacting to structure R by its para-substitution. You can go to actually, if your X is going to be a strongly electron withdrawing group, you can move reactions yield up to 62% from 42. That was amazing. He later actually expanded this. This is his outcome. I just wanted to show if you are going to do this multidisciplinary approach, and actually you can learn from computation or designing principles, go to lab, open new reaction. He actually opened new reaction types, catalytic reaction, and his groups still are using, even he graduated and move on. Another problem which I want to quickly bring to your attention is actually some things from my renewable energy project. I know that in Azerbaijan economy, it's critical, it's renewable energy. And I put here just this outcome from this DOE's websites, and I have DOE grants, I have access to DOE's materials. And renewable energy actually only it's 11% in 2020, part of entire energy which the world is using. But this from 11, mostly it's comes biomass, 43% from 11. Wind, I mean, in Azerbaijan extensively you're using it's actually wind energy or hydroelectric water. But solar contribution is only 9%, 9 from 11. Even solar, we have huge solar energy. Yeah, why not to move solar energy and use this abundant solar energy? For this reason, I mean, there are several ways people are doing in the world to utilize solar energy. Of course, there's one is just to put the photovoltaic panels up. A lot of people are doing, I am sure in Azerbaijan they are doing, especially on countries where it's you have a lot of sun. Problem is you cannot use solar energy. You need to find waste storage of this solar energy. It is not permanent. I mean, nighttime, you cannot get, the winter is going to be very low. You need to find a way to convert solar energy, some different type of energies, and really save it. Then use later. Photovoltaics percentage actually efficiency is very low. It's a bit below it is actually, if you're using silicon panel, it's going to be theoretical levels is 17%. But this process, this project open new ways, and people come up perovskite solar cell, new material design, or new materials polymer design. I'm sure it's, you know, what's from where it comes, perovskite. Perovskite comes from this academic Perovsky from Russia. He described as actually mineral. Structure is this mineral is similar or same with perovskite, new material which people come out. For perovskite, if you will look, if anybody is doing perovskite design, etc., you can see for 1 year, they may got these citations, is thousands. Really, it's very hot area. And that's because application to energy mostly. Of course, another direction is really store the solar energy as in battery, then use as a batteries. And now it's a lot of people are a lot of technologies using batteries, solar, but you can use actually solar batteries. Use lithium, it's cobalt, nickel, but still it is using these really expensive metals. But also density of energy which you are saving, it's not very high. And we move to different direction. We want to actually study its solar to chemical conversion, because if you can convert solar energy to chemical energy, use this chemical energy later in a way we are using it for some hydrocarbons. For that, you need to really find this it's abundant materials which you will use for these purposes. Solar energy abundant, and you need abundant and at the same time green, because you want to have this clean reaction. That's actually comes to water split. You can use water split under solar light and to get protons, and oxygen goes out. Then this proton you can either to reduce to H2 molecule and storage H2 molecule, use actually hydrogen fuel, or you can use a proton and the nasty is carbon dioxide, and to really convert carbon dioxide to carbon-based materials and use as a fuel. That's what actually we have funding from the OEO this almost 20 years. We're working on this area. We have done so many different type of things, but this is really complicated designing process. For example, even this left-hand side, this electrode, it has 3 components. You have sensitizer, and you have water oxidation catalyst, as well as reductant. It could be nanomaterials, or could be quantum dots, or semiconductors, etc. Sensitizer actually catch solar energy, then there splits, extons, you go to the oxidized water catalyst. Water catalyst takes the water and oxidize, rearrange the splits, you get protons, then you transfer protons there. And this is difficult process. First, an in-water oxidation catalyst should be stable. If you have oxidizing environment, it is very difficult to get stable catalyst. Really, you need to really find stable water oxidation catalyst. In another word, catalyst design is going to be a strong component of this. Second is, it's actually highly effective reductants you need to get. Today, people are using these quantum dots mostly, or semiconductors. We have done these quantum dots. My colleague, Tim Liang, he is physical chemist. He is more working the quantum rods, quantum dots. I've collaborated on this. Craig Hill, and he is actually an inorganic chemist. Mainly it's water oxidation catalyst, and putting it together and ongoing this dynamic processes, etc. studied from computation or machine learning and passing information around. That's how we are 3 groups. We have this every week group meetings, sharing knowledge, and students are really developing as multidisciplinary students. And they can do a calculation. They can go to lab to do this, at least simple theoretical people can go to do simple experiments, and same as experimentals can do calculations. But this is actually, it's one place. Actually, I said we also design new methodology, computational methods, really to look at the interfacial electron transfer or electron transfer dynamics, exton generation, exton splitting, etc., etc. I don't want to give too much information there. And I just want to say that we got 2 patents on these directions. So far, we developed the polyoxymetallate base. This is tungsten oxides or molybdenum oxides, etc. It's the D0 metals with oxygen. And we use this polyoxymetallate as a template to build this catalyst packet. First catalyst which we published is 2008. It has the tetra-ruthenium catalyst. It is cited to 611 to 10 times, but nobody wanted to use it because it's expensive tetra-ruthenium. Then we use, actually, it is a similar approach to put together tetra-cobalt polyoxymetallate catalyst. But on this polyoxymetallate, internal atoms are also, we call this heteroatom, critical for stability of this cage structure. Our first catalyst which we developed inside, we published in Science, it was silicon inside. Then from computation, we learned that this catalyst, first catalyst, shows some instability, especially when you go to electrochemical conditions. Then we decided to go to actually improve stability, replace silicon by phosphors. Computation, not phosphors, by its transition metals. Computation shows that if I will put there transition metal, for example, vanadium, it will have the similar orbitals as cobalt, 3D metals. It will bring this additional stability. Amazingly, when we did this is 2014, and finally it's experiments were proved. We got. Could you please actually it's mute your microphone? Would you please mute your microphone? We did that actually. So we see vanadium analogous is. I mean, it is about 100 times more reactive. I mean, produce more oxygen. And now we are moving this to projects. I don't want to go too much details. We use actually poloxymetal as a template to build actually structurally dynamic photooxidation catalyst. You remember it's actually photosynthesis, actually active sites, manganese 4 or 4 part. It is not stable. It does electron reaction, then destroy itself. After reactions done, it's repair. There is repair mechanism. We want to mimic that. We have done this actually. It's always 6 iron centers there with three poloxymetalate. Unfortunately, it didn't show catalytic activity. Now we built this cobalt nickel. For 2 cobalt, 2 nickel catalysts, we would really put in together entropically stable or high entropy species, which is going to be to do water oxidation catalyst. And indeed, we expanding this parameter space. Indeed, we have shown that this dicobalt dinickel catalyst show significantly higher catalytic activity than original cobalt catalyst, cobalt 4 catalyst. We are moving these directions, and I don't want to really take more of your time, but also I want to bring your attention 2 things. One is science now is going to mostly computational science, etc., quantum directions. You have heard a lot. I am not working on that. I'm just bringing this to your attention. And if you heard that a lot of quantum information systems, quantum materials, or etc., and we are interested in quantum computers. Today, if anybody will get better working quantum computer, quantum information systems, they are going to own future. And after we having this, all your previous security things or military things, etc., going to be absolute, because everybody can break your password and to take over everything. Because quantum computers, they are going to be thousands times more faster than existing digital computers or classical computers. And that's why they call this quantum supremacy. I should provide additional support what I'm saying. And now US has put in almost 20 billion on this research. If you have idea, you know how to do it, go ahead, its money is available. Same thing in China. I mean, the ongoing competition between, so discussion between China and US, mostly now ignited by quantum information systems. This is one direction. You just need to, if anybody is interested, you can keep your eyes on these developments. Second one, there are also people are talking to me when I'm talking about machine learning or deep learning type of things. They always keep telling me, Jamal, if you are doing methodology or people are doing methodology, machine learning, etc., they can do everything better than chemists. Why we need to go to lab to do labs work? I think this is wrong. And in order to show this wrong, I put together these fancy pictures together. And left-hand side, if you visited Rome, is Vatican, it's a Sistine Chapel. There is actually this picture, Michelangelo, where the God is passing knowledge, or it's to man, his knowledge, and it's to man. But he's passing, he always controls man. He said, a destiny. Same thing is the right-hand side. If man pass knowledge or control to a machine or machine learning, it doesn't mean machine is going to take over, because man is going to be in charge always. And always anything comes from machine learning, you have to go to lab to really it's actually prove or validate it. And that's don't afraid, and still this lab is going to be exist. Or chemical reactions and experiments is going to exist, and also it's a long way to go into really rational designing. This takes a lot of efforts. And in this stage, I would like to thank this actually to my group members who works on the left-hand side, my collaborators. I don't want to go to everybody, and also funding. DOE and National Science Foundations, and also military foundations in the US. I didn't talk about that. And thank you for your attention, for listening my gibberish.